we want to turn this data collection problem into a data generation problem.
What was your biggest takeaway after completing this paper?
My biggest takeaway is that every single part of the system is entirely important.
What do you think is the ideal form of data?
The great thing about it is that compared to the first two, it can generate a ton of data much faster and more efficiently. How the robot should recover when it hits failure modes. For example, if you give the robot a hard kick, it's already completely OOD. Can I just ask anything?
Feel free to ask anything. Hello everyone, I'm Xin Yun from the EAI Times.
I think this is the first time I'm meeting you all in a non-written format. This is a brand new podcast called EAI Aha. Why this name? Because in my years of writing, I've always loved chatting with young researchers. Their deep insights always give me that, so that's how it is aha moment. And besides that, I think the rapid development of embodied AI lately is also inseparable from these aha moments. So EAI Aha is essentially about capturing those moments and breakthroughs that change how researchers think and do academia. Every breakthrough starts with a question, a conversation, or a sudden spark. We record these moments before they become the future of embodied AI. All right, thanks to our first guest, Yen-Jen Wang. Now, let me introduce Yen-Jen's background. He is a second-year PhD student at UC Berkeley, co-advised by Peter Abil and Shankar Sastry. During his undergrad at Tsinghua, he was advised by Junyu Chen. So let's welcome Yen-Jen, and please introduce yourself and say hi to everyone.
Hello everyone, my name is Yen-Jen Wang and I'm currently a second-year PhD student at UC Berkeley. Actually, I'm about to start my third year, my advisors are Peter Abil and Shen Gu. My main research focus is embodied AI and motion control for humanoid robots. Recently, during my internship at Amazon Robotics, edition EAI, I work on a paper called VLK. The main idea is to reconstruct the real world to generate humanoid robot data at scale, making it easier for robots to learn various tasks. Yeah.
Great, thanks Yen-Jen.
Yen-Jen has made significant contributions to both dexterous manipulation and humanoid robotics.
And we've covered some of his other work before. So today we'll focus on this core work, VLK. First, I'd like Yen-Jen to briefly summarize what problem VLK is solving and how it solves it. Just a one-sentence introduction.
One sentence, okay. So the core idea of VLK is that we want to turn the data collection problem into a data generation problem. How to generate this kind of data ourselves. Right. And our approach is basically to reconstruct real-world scenes to automatically generate this data. This data includes vision, language, and the robot's whole body motion. Then, based on this data, we can train a policy that condition on vision and language and outputs kinematics. Once I have the policy and a local tracking policy, I can translate those kinematics into actual commands for the robot to execute. That's our VLK.
I think that's a very concise summary. Of course, there must be a lot of details to share about this paper, so I'll hand it over to Yen-Jen to give us a more detailed introduction to the overall concept and setup of VLK.
Sure, no problem. I've prepared some slides, so let me share my screen. I'll present our VLK work. Before we start, I can show a highlight video first.
Okay.
With VLK, we can input language instructions and the robot can perform the corresponding tasks in the real world. Right, this does not include navigation. It includes tasks, such as moving boxes. This is the project I did during my internship at Amazon Robotics. I'm actually still interning at Amazon. Right, so our main idea is that we want the robot to have a policy, and then we condition it on our language instruction. So the robot knows what it needs to do. But at the same time, the robot also needs to have perception capabilities to see what the real world looks like and then complete the corresponding task based on the instruction we give it. And then here, if I want the robot to complete this kind of task, it's obvious that I need my robot to have vision to perceive the world, and I need language to control the robot so it knows what it should do. At the same time, we will output the kinematics, which refers to what the robot's actual movements look like when it executes them. And then once the robot knows what movement it actually needs to execute, it can just go ahead and do it. Right. And then
I'll interrupt with a quick question here. I want to know about kinematics, for example, because there's also feedback from corresponding objects. So what are the core ideas of our target kinematics, and how does it handle dynamics? Could you give me a brief introduction? Yeah.
Sure. So I think before answering this question, we probably need to clarify what kinematics and dynamics actually are and what the difference is between them. Generally speaking, if I make a movement, like say if I go dancing or something, what you see of my movement itself is actually kinematics. Then what is dynamics? It means that we take physical properties into account. I think the main difference between the two is whether we consider various physical properties. If we don't consider physical properties and it's just the movement itself, then it's kinematics. But if we consider physical properties, for example, with a robot, each of its motors will have some friction and internal parameters, and there might also be the influence of physical parameters like the robot's own inertia and gravity. If we take these into account, then it's a movement that complies with dynamics. So I think the biggest difference between kinematics and dynamics is whether physical properties are taken into account. In plain terms, that's helping
Yeah,
context.
okay.
I hope that answers the question.
See. Yes, it does. But I'm quite curious, how do you handle dynamics in this kind of framework? You'll talk about that later, right? Yeah.
Right. I'll get to that later. We'll have a whole body tracking policy, and it will convert a kinematics command like this into low-level motor commands for the robot. Yeah.
Okay, no problem.
Before writing this, there were actually already many different forms of data, and I think each type of data is great, but they all have some shortcomings. For example, we can do real-world teleoperation, which is very powerful. We can collect all kinds of data, and after collecting it, we train a policy, which is very powerful. But the problem here is that when I want to teleoperate, it relies heavily on a human to teleoperate the robot, which is quite time-consuming and difficult to scale up in a short period of time. And the second type is motion capture data. I think motion capture data is very good data, but while it's very good at the kinematics level, it lacks the corresponding egocentric perception information, and it also doesn't have language instructions. Simply put, if I want to use these instructions for a robot, the robot can use this data to do some motion tracking, dancing, and all kinds of tasks, but it will be difficult to do local manipulation because it can't perceive the world. In other words, the dataset doesn't include the ability to perceive the world, right? And the third one is that we can train entirely in simulation and do sim to real. I think this is a very, very good method, but it relies on, first, there's the RGB sim to real gap, though this part has been solved quite well in many papers now. But I think another relatively difficult part is that if I want to use reinforcement learning to solve a local manipulation task, the difficulty lies in the fact that I might need a lot of complex reward designs. For example, for a task, let's say I want to grasp an object first, it might be divided into several stages. I might need to design the first stage reward to be the robot getting closer to the object. And the second stage is, getting the wrist next, getting the robot's wrist close to the object and grasping it. You might need to set the reward in multiple stages, which is relatively difficult. It's doable, but it's just a bit more troublesome. Right, and that's also why we might want to propose a method like VLK to generate more data, which is relatively easy, though it also has some limitations that we can talk about later. Right. So our idea here is mainly that we divide it into several steps. The first step is, in the real world, I first take an iPhone and scan a real world scene and reconstruct it as a 3D Gaussian splatting representation. And then I have some graphics methods where I can generate a lot of different motions and interact within the scene. Once I have this motion, I can generate the corresponding ego view and train a policy. Finally, I add our motion tracking policy and deploy it in the real world. Right, so the pipeline of our entire method looks like this, and it's divided into two major parts. The first is how to prepare this data, and the second is to train our policy and deploy it to the real world.
Yeah.
Let me first quickly go through the first part, which is our data generation part. Right, as I just mentioned, first of all, we'll take a phone. Of course, we can use all kinds of equipment and scan our current scene. After we finish scanning, we can train a policy to reconstruct our 3D Gaussian splatting. Right, and the effect of 3D Gaussian splatting is actually very realistic. We can show some demos of our dataset later for everyone to see. And then, after scanning this scene, I might need to generate some waypoints. What do these waypoints mean? It means, say, my robot, I want to execute a task now, so for the robot's initial position, I can randomly sample an initial position in this environment, and then I'll have a target position the robot wants to reach or something it wants to do, where it should go next. So it's equivalent to having a start position and an end position. And then, now that I have this, how do I generate a collision-free path, which is a path with no obstacles in the middle, so the robot can walk along this path? Right, and at the same time, if I want to say carry a box now, I'll definitely have some additional conditions. For example, I need to know where my hands should be placed based on the position of the box, so I can generate a set of waypoints based on these things. And for these waypoints, we can use algorithms like A star or some shortest path algorithms to solve this waypoint generation problem. And then, now that I have these waypoints, and at the same time I also have some conditions, for example, if I want to carry a box, I know where the box is, and I know where my hands should probably go to pick up the box. Then I can batch generate this motion. Furthermore, now that we have the corresponding language and our motion, I might want to put this motion into the simulation. In this simulation, our scene is actually the Gaussian splatting scanned in the first step, so it's very realistic. And I can render the RGB image that matches this motion. At the same time, we'll make sure that the perspective and various information of this RGB image in the simulation are aligned with the actual sensor position of the robot. Right, of course, just rendering it directly is still not enough. We still need to add some randomization to solve some sim-to-real gaps. So, we'll randomize our lighting, we'll randomize our colors, and at the same time, we'll also randomize some camera intrinsic and extrinsic parameters. Extrinsics include the camera's position and orientation, its position and tilt angle. We'll also randomize some of the robot's internal parameters. Right. And here is a video that shows what the visual effect looks like with and without randomization. The one on the right shakes a lot because the camera has some extrinsic randomization, so it shakes quite a bit. Right. Okay, and then, as I just mentioned, how we generate this dataset. I'll show you what this dataset looks like after it's generated. We can look at this image, which is a navigation task, and we have two different scenes to show you here. One is a more home-like scene, and the other is a lab scene. Right, and after we finish scanning with Gaussian splatting, it might look like this background. At the same time, in the top right corner here is the robot's egocentric view, which is equivalent to the perspective the robot sees. And we render it in the simulation, which looks roughly like this. Right, so this is what our dataset looks like, and at the same time, its corresponding language instruction is here. And the next one is putting down a box. Right. Then there will be the corresponding egocentric view where you can see the box, and at the same time, the robot will also have some of its kinematics motion here. And then now that we have this data set, we can train our policy, which we call the VLK policy, Vision-Language-Kinematics policy. Right, so we have a policy that takes an egocentric image, language, and the robot state as input and outputs the robot's kinematic motion. Right, so let's go step by step. As I just mentioned, I'll input our egocentric camera information, and we'll have our current language instruction as well as the robot's current state. The robot state will include the following. This is mainly during training, right? And later I'll slightly distinguish between training and deployment. During training, actually, I missed something earlier, which is that our dataset actually includes the contact of the robot's wrist part with the object. And this contact is binary, meaning it's 0 and 1, representing whether my left wrist and right wrist, respectively, have contact with the object, right? And then during training, I'll also take this into account. Our robot's kinematic state includes the robot's current root velocity, which has x, y directions, and its yaw direction, which is the lateral yaw direction, right? At the same time, it will have the height of the robot's root position, as well as what the values of all the joint angles of my robot should be. And here, the joint angles are represented by sine and cosine. Right, and at the same time, as mentioned earlier, we'll have this wrist contact and we'll put these in training. During training, wrist contact is included as an input. During deployment, the actual wrist contact is unavailable. So the previously predicted contact is fed into the next step autoregressively. Right.
Yeah.
And then since I have this data now, I can train a policy. For this policy, we fully fine-tune our PI 0.5 model. Yeah. Of course, if we just fine-tune it directly, there will be some issues. For example, the motion we generate might not look physically plausible. Like when hugging a box, the robot might find that, hey, my root position is stationary or slightly lower, but my feet are completely off the ground. When I bend down, my feet are actually off the ground, which doesn't really make physical sense. Or say when hugging a box, actually I'll split the dataset into my training dataset and validation dataset. Then when I validate on the validation dataset, I might see the issues I just mentioned. First, the feet leaving the ground, and second, the wrists not actually touching the box. Right. So during training, we actually add some auxiliary losses to handle these issues. For details, you can check the appendix in our paper. It's written there.
Yeah. Can I interrupt and ask a quick question?
Go ahead.
Why are there these physical deviations?
Because the task I'm considering right now is actually a local manipulation task. What I care about is first, whether I'm actually making contact with the object, and also whether my wrists are placed in the correct positions. And of course, if I fine-tune this PI 0.5, it can also learn a similar motion. But mainly because I'm working on a manipulation task, I might have higher accuracy requirements for all of this. Right, so I need to add some extra auxiliary losses so that the wrist output can be better and align more with some key visual information. And then regarding the issue of feet leaving the ground that I just mentioned, it's mainly because if I want to feed this motion to my whole body tracking policy later, it might not perform as well. But actually, this kind of issue itself doesn't have much to do with fine-tuning PI 0.5 itself. They are extra issues introduced, right?
To follow up a bit, I'm also very interested in your losses. What dimensions did you consider when designing the losses? Could you talk about that too?
Oh, right. We definitely have the flow matching loss from PI 0.5 itself. And at the same time, we also considered, because I want my feet to be on the ground and I want my wrists to be hugging the box, we have to add this forward kinematics loss. This is equivalent to saying I can convert all my current joint angles, the joint angles output by the policy, into the positions of my two wrists and the positions of my two angles, and I want these angle and wrist positions to be closer to the data, meaning the data set. It's like I have an extra signal for supervised learning to do this.
Mm.
But at the same time, I have some other losses to handle, like foot sliding. When I'm walking, my root velocity might move, right? I'll output my root velocity in the XY direction, but this movement speed in the XY direction might not align with my foot movement speed. And so I'll add some losses, hoping it can align them like this.
Yeah. Okay, got it. Great. Sorry for interrupting. Please go on. Yeah.
Right. Also, our policy's output is a 1-second future trajectory, but it also contains some of the information I just mentioned. And finally, I'll feed this output. I feed the kinematic trajectory into our whole body tracker. We use SceneBot, which is a strong global general motion tracking policy with contact labels. And I will mention about the global part and the contact part. Global means that when I'm running a policy, it actually tracks my route position and route orientation in the world coordinate 的这个位置。然后content label means that during the operation, I'll adjust some of my motion tracking behaviors based on this contact label. For example, when I'm lifting a box, if I have a box now, my hands might just reach the surface of the box, just barely touching it. But the box can't be lifted like that because it might have some weight. And if I just touch the object, is like if I really want to lift the box, I might need to apply a bit more inward force to like clamp the box before I can lift it up. So at this point, if I have my policy, it can judge how to adjust my behavior based on whether I currently have contact with the object, which will be more beneficial for me to do some manipulation tasks, right? So actually in our experiments, we showed that, hey, if my policy doesn't consider contact labels and just does general motion tracking, although it looks like I want to lift the box, in reality, I can't lift it. It was only after I took this contact label information into account and let the policy adapt to this behavior that it could lift it.
Mm-hmm.
And what our whole body tracker mainly does is previously I might have had some kinematics targets where my robot would tell me, hey, my motor should actually move to such and such a position. But because there are many internal motor parameters, and at the same time, there will be, including what I just mentioned, like friction, motor damping, motor armature, and also maybe the influence of some of the robot's inertia. So in fact, we need a policy that can convert such a kinematic motion into the actual commands executed by the motor. And that's what our whole body tracker does, right? And of course, this global tracking policy definitely relies on some state estimation to let us know our position in the world coordinate system. And for this state estimation, we use super odometry, right? And I think both SceneBot and super odometry are very good works, and everyone can check them out, right?
Mm.
And then I'll show some real world results, right? And navigation, which is walking to all kinds of different obstacles here, like, oh, sorry, different objects. This video is shown at normal speed. And then as we were doing the experiments, we felt, hey, doing normal experiments is too boring. Can I like stir things up a bit? For example, I think randomly placing the robot's position doesn't count. That's very normal. But one thing we did was, hey, can I, because in the simulation, we didn't actually have this case of a white chair on a table. So I thought, hey, if I put it up there, can the robot follow our language instruction, like walk to the white chair on the table? Can it really walk over? And we found that it actually could walk over, right? So we did some of these scenes that might not have been seen in the simulation, in the training data. Right, and at the same time, we have box lifting, and it can lift boxes of different sizes. Right, during this process, we can actually adjust some of the language instructions we give to the robot. So like at the beginning, we tell the robot to lift the box, and later we tell the robot to put the box down, right? And at the same time, we can also do that kind of like multi-stage, and including lifting the box, then navigation, and then putting it somewhere.
I have a quick question here. Are these different box sizes in the dataset, or can it generalize to boxes of different sizes?
In our data set, we trained on all kinds of boxes with all kinds of different appearances, right?
The power of simulation.
Right, the power of simulation. We considered a whole bunch of different box assets and did rendering. And then our policy can also resist some disturbances, including me moving the obstacles in real time or under disco lights. One day when we were in a meeting, the Amazon advisors, they said, hey, okay, let's go check it out. And then they said, hey, can we see if your policy can work normally under disco lights? So we tried disco lights. And actually, both of these videos have disco lights. And basically, they can work. Of course, disco lights might slightly affect some of our policy's performance. But basically, the tasks can still be done, right? Compared with normal lighting, the robot may not walk as well under disco lights, and there might also be some minor flaws when putting down the box, right? But overall, the policy can run. Right, of course, when training, we didn't have disco lights. And here are some long horizon demos. And right, which includes this kind of box lifting as well as navigation. Okay, and that's about it. Let's see if you have any questions. Feel free to ask me.
Okay. Thank you very much. I feel like hearing it again gives me an even deeper understanding of this paper. And next, there are some quick questions maybe we didn't have time to ask just now. Let's discuss them together. Just now, you actually introduced a pipeline from reconstruction in the real world, then this to, for example, to egocentric rendering, and the whole pipeline like this. And I'm quite curious, what is the biggest difficulty in this pipeline? Or maybe I can ask it this way. I understand that the sim to real gap is the biggest difficulty, but we often treat the sim to real gap as a single problem. If you were to break down the sim to real gap into different gaps, how would you break it down? And how did you solve it in this pipeline? Yeah.
Right, actually, because our system is a composite system, it contains a lot of modules. So its difficulty is actually an intersection of 3 parts, which includes perception difficulties, hardware difficulties, and also some difficulties in dealing with the environment. Right. And for perception, I feel the first and easiest one to think of is this RGB sim to real. Right. And of course, there have been some previous works doing this RGB sim to real, but we did encounter such problems. And so I mentioned just now that we added different levels of randomization. And then another one that wasn't mentioned just now is actually our motion blur. This part, right? For example, because it might be different from some tabletop manipulation, when I'm doing humanoid, like whole body movements, for example, if I want to lift a box, I have to quickly bend down and lift this box up. Then at this time, or when I'm walking, I might have some oscillations, and these might cause motion blur, which means that what my robot sees, the RGB image is actually very unclear. Right. And so we have to solve this motion blur. And the simplest idea is, hey, when I'm training this VLK policy, I'll add a whole bunch of motion blur to this RGB image, right? Because actually the real world sometimes causes very severe motion blur. So I can also add such motion blur during training. But we found that, hey, if we add a lot of motion blur when training this VLA policy, it might completely lose the semantic information of this image. Because we are fine-tuning pi 0.5, it only conditions on like a single frame of, it conditions on maybe just a single frame of the RGB image. So in this case, adding a lot of motion blur actually has a huge impact, and it can't even align this RGB image with my language instruction. So our approach is a two-way approach, which means we do some things during deployment and some things during training. We do add motion blur during training, but we don't add too much. We just add a little bit. So basically, when we look at it, we can still see what the semantic meaning of this RGB image is. During deployment, I keep a 0.3 second image buffer. And before I feed this image to our VLA policy, I'll select the clearest one from this image buffer, which we calculate using the Laplacian score, and then take out this clearest image and input it to the VLA. And in this way, such a two-way approach can significantly reduce the impact caused by motion blur. Right. Right. And then the second part mentioned just now is probably about hardware and deployment issues. And we'll find that, of course, converting this kinematics into dynamics itself has a certain problem. At the same time, when I'm deploying, some system latency is also very critical. So we used a real-time VLA for deployment together with test time RTC to ensure that during execution, everything is as continuous as possible and the latency is as low as possible, right? And for RTC, the full name is real-time chunking. And I can explain it a bit. What it mainly does is, say I have, let's assume my policy outputs action chunks. And after I execute the first action chunk, I might go to predict my next action chunk. And there will be a period of inference time in between, which is the inference time. And during this inference time, the robot might actually track its previous action, right? But in humanoid robots, if I track the previous action, like I might stop at the previous action. But if, say, my previous action was standing on one foot, because during walking, sometimes one foot is in the air and one foot is on the ground, right? At this time, it might not be in a stable state. So if you track such a time, like tracking such a motion, it might not be ideal. Right. So at this time, like I would hope I can compress this inference time as much as possible, right? But I compressed, so I used real-time VLA. But after compressing the inference time, I found that the motion still did not look natural. So we did this test time RTC. Test time RTC means we can, before the previous action chunk ends, make the prediction in advance so it goes to the next action chunk. And there will be some overlapping parts between the two action chunks. And I need to make the overlapping parts as close as possible. Right. And then, yeah, the third part is about my environment, where I need to do scene reconstruction and motion synthesis. For scene reconstruction, I need to do real to sim, which means like I need to scan my current environment really well to train a good Gaussian splatting. And at the same time, I need to make sure that the scale of the scene in simulation and the real world is the same. Right. Even though I'm using simulation data, if the scale of the scene is different, the rendered RGB images will definitely look different in terms of object sizes and the relative positions of the robot, which makes it very hard. It could cause some sim to real difficulties. So we need to calibrate everything properly. Right. And that's basically the main difficulty of our pipeline.
Okay, got it. I have a few follow-up questions, some of which I might not have fully understood. You just mentioned motion blur and latency issues. Can I assume these are problems that humanoids need to solve more urgently compared to tabletop manipulation?
Yes, because a humanoid is a relatively highly dynamic system. So when it performs certain motions, I mean, tabletop manipulation can also have motion blur issues, but they might be smaller compared to humanoids. Right. For humanoids, first, there are vibrations when walking, which cause motion blur. At the same time, when doing whole body control, there might be some fast motions that also generate motion blur, so it's more severe than in tabletop manipulation.
Is latency also a more difficult problem for humanoids?
For latency, I think it's mainly because during operation, if the current policy stops anywhere and does nothing, the humanoid will actually fail. For example, when we used to make the lowest level RL controllers, if we added a delay, it was like the robot just froze in midair and would fall right over. Since it has no real-time feedback, it would probably just fall to the ground or fall over. Right. But for a manipulator, like a pure robotic arm, it's basically relatively static. And it can stop at any point without any issues. But if you're talking about, say, in-hand orientation, like rotating objects, there might be some differences. Right, but for most manipulation tasks, they are indeed relatively static. Right.
Yeah, okay, I see. You mentioned RGB sim to real just now. Let me ask a beginner question. We often hear about the sim to real gap. What's the difference or connection between this RGB sim to real and the sim to real gap we usually talk about?
In the past, when we did sim to real, we mostly considered the sim to real gap in terms of the robot's own dynamics. So we focus more on the physical properties of the motors and the robot's body. And we would add our solution, whether for RGB sim to real or the sim to real we talked about before, is always to add randomization, because we actually have two different domains, the real world and simulation. And we want to add randomization to their corresponding properties to bridge the gap between simulation and the real world. Right. Essentially, we add randomization at the sensor level. It's just that we have different sensors. like when we did sim-to-real before, the sensor we considered was the robot's motor, and now that we do RGB, we consider the camera. They are both sensors, just different types, right? And then because of the different sensors, the dimensions where we need to add randomization will also be different. Right, so if you ask me, I'd say the underlying solution is the same, which is to add randomization at the sensor level, right? It's just that because the hardware itself is different, the dimensions and properties we randomize are different, right?
Yeah. Okay, I see.
Yeah.
And I think I pretty much understand this question. Regarding the RGB sim to real gap issue we just discussed, you also mentioned that there's actually a lot of research being done in the industry. I'm quite curious to know what foundational or milestone works you think are supporting the current success of VLK behind this real RGB sim to real. Right. What are the academic advancements in the industry? Yeah.
Right. One of the earliest examples was on dexterous hands from Ankur Handa's team at NVIDIA's Seattle Robotics Lab, which worked on RGB sim to real for dexterous manipulation. And right at that time, they basically added enough randomization to make it work. Then last year, NVIDIA Gear, the lab in the Bay Area, came out with 2 papers on humanoid sim to real. One was viral, and the other was doorman, right? Firo was mainly about like having 2 tables and picking up an object from table A and putting it on table B. And doorman was mainly about doing various door opening tasks, right? And they both applied this RGB sim to real to humanoids. So seeing these works gave us more confidence that this RGB sim to real can actually be used to handle the rendering of our synthetic data, right? And indeed, we did that and we made it work, right?
Okay. And the next question is, another question is, I think active perception might be more common in manipulation, but I don't know if it exists in humanoids. In manipulation, some research focuses on, say, the extra information input brought by head movements. I wonder if active perception is also something that needs to be solved in humanoids, or if it's a technical trend, and what do you think its difficulties would be?
Yeah. I think this is a really good direction, and humanoids can definitely do this active perception. And yeah, like what Yen-Jen did before with Twist 2, he basically took the G1 head, which is normally fixed, and added a servo motor to it, turning it into a movable camera, right? And of course, for active perception in humanoids, the main thing is that since the humanoid itself can move, we can actually adjust the humanoid's body to change our perspective. Of course, if our humanoid's cameras are quite limited, like in terms of quantity, then when walking, I might sometimes need to focus on, first, the target object I'm interacting with during the motion, and second, the terrain I'm currently moving over. Just like when we humans walk, if I want to go grab something, I'll definitely look at where the object is, but at the same time, I'll notice if there are any obstacles near my feet. Right. I think if humanoids are going to introduce active perception, this is probably the main area to consider. But actually, many robot companies now put a lot of cameras on their robots. Some might point directly at the floor to look at the terrain, while others point forward. Of course, sometimes you might have situations where the camera's field of view is quite limited, and that's when you might need active perception. Right. Like before, when I was at Professor Chen's company, when we were doing teleoperation or collecting real data, if the robot's head was always looking straight ahead, it was sometimes hard for it to see objects on a table. So in those cases, we had to adjust the robot's head slightly downward. Right. Maybe there are some factors like that involved.
Yeah, okay. Another quick question I've always been curious about, is it actually harder to handle some of those critical manipulation phases? For example, when bending down to pick something up, the motion blur might be really severe, but that's a very critical moment. Or when manipulating something, there might be occlusions, which is also a very critical moment. for these core critical moments, how do we usually handle them? Do the issues I mentioned actually come up? Yeah.
Right. I think we first have to see if this kind of situation occurs in simulation.
Yeah.
And if it does occur in simulation, like visual occlusion and things like that, then it's actually relatively easy to transfer to the real world. So the issue should be relatively minor, right? But if it doesn't happen in simulation, but does in the real world, like motion blur, and say it's something that can't be avoided through twist 2, hypothetically, then one approach could be to do some processing when generating this data. For example, I could make the motion itself slower. Like when bending down, I can adjust the speed of the bend when generating that data. Right. And yeah, I can change some of my data distribution. Since I'm still conditioning on the output of this VLK policy, I can make some adjustments in the training dataset for the VLK policy to, avoid some of the potential issues.
Yeah. Okay, got it. Very clear. Yeah, right. Just now on another quick topic, when talking about VLK, we introduced a concept called dynamics kinematics. My understanding is that your overall solution is to separate the two and then combine them using contact labels. I'm quite curious, why did you choose to consider kinematics and dynamics separately back then? What was the thinking behind that? Yeah.
I think there are a few main reasons. The first is the issue of inference speed, right? If I want to have a higher level policy that has a good representation, like a good vision representation and a good language representation, and we need to output a robot action or kinematics motion, then the model itself is going to be a certain size. In that case, if I want to output a very low level humanoid command directly, it might be quite difficult. Because the inference time is long, the humanoid might just freeze in place. Since a humanoid is a highly dynamic system, we want to have very fast feedback, right? So for humanoids, we probably need to split the system, right? So the first reason is this frequency issue. And then if we split it, there are actually many different ways to do it. So why did we consider this kinematics motion? I think one of the reasons is that kinematics motion is a more general representation, and in many graphics methods, it can solve some of the kinematic level problems quite well. And also, it's actually very easy for us to get this kinematics data. For example, we can get mocap data, and we have kinematics engines that can generate this kind of motion data. At the same time, we can also extract human movements from videos, which can also be in this data format. So it turns out that kinematics data is relatively easy to obtain.
Let me ask a beginner's question. Is there a clear definition of layering in humanoid robotics?
I don't think there is, actually. Right, everyone has their own way of layering. For example, there was a paper before called Leverb, and its layering approach was like, hey, I can still have a high-level policy and a low-level policy, and I'll use this latent space to bridge the two. Right, and of course, in our VLK is a high-level policy, and we have a whole body tracker, which is a local policy. The way we bridge them is by taking this whole body motion reference, which is a kinematics motion reference, as a high-level output to bridge the two, right? So everyone actually has their own different way of defining it, so there isn't really one clear definition. Right. Of course, I think one of the reasons for layering is whether you have a representation that is more suitable for a high-level model to generate. For example, this kinematics motion is a very good representation. So that's the first reason. And the second reason is that for a humanoid, it's a system with very high frequency requirements. But for some high-level policies, the model itself is quite large, so it's difficult to have it output at a very high frequency. So based on this frequency consideration, some people will split it into high-level and low-level policies.
Yeah. Let me ask a follow-up question. Some people split the humanoid into two layers, the upper body and the lower body. Do you think that's a different way of layering, or is it quite similar to how you classify it?
I think to some extent, splitting it into upper and lower body is essentially a key point representation. For example, the center position of your robot and the wrist position and orientation of your two hands, right? And to some extent, it's a type of key point. And for our VLK policy, what it outputs is also a type of key point, except our key points contain whole body information, so it can give the robot a more comprehensive representation of its motion. Of course, there are some that are in between, like our 3-point policy or 3-point key points, and also 5-point. 5-point probably refers to something like twist 2, where I consider the robot's base position, wrists, and ankles, right?
Yeah.
And for those older policies that split the upper and lower body, a lot of times we might use a velocity command to control the robot's center position. But actually, once you integrate that velocity command, it's also a key point belonging to the center position. So I think essentially there's no difference.
Yeah. I see. That leads to another question I'm very curious about. In the long run, do you think kinematics will be a more general representation across different embodiments, or would something more latent or implicit be a more general representation? Yeah.
I feel like I don't really know the answer to this question. Right. I think if it's latent, then it lacks some explainability or interpretability.
Yeah.
Right. But on the other hand, it might be able to bridge the high level and low level more tightly if we train it well. Right. But for kinematics, although it's more intuitive and easier to explain, and we can verify at the kinematics level whether our output is correct. But it also has some inherent issues. For example, when we design, like right now we are considering rigid bodies carrying boxes, but if we are not considering rigid bodies, but objects whose state can change, like deformable objects, like cloth, origami, or things like that, it's actually very hard to represent the state of these objects using kinematics. And then it becomes very hard to use kinematics as an intermediate medium. For example, if I want to, because right now, yeah, if it involves things related to force, then it might be quite difficult, right?
And I know VLK has a very important point, which is the contact label, which you also just mentioned. I'm quite curious, what was the original intention of doing contact labels, and did previous work touch on this area?
Right. Actually, for previous motion tracking policies, most of them basically didn't consider contact labels at all. So why did we consider contact labels? Actually, it's like this. When the robot needs to interact with an object like carrying a box, if I only track the motion reference, it's very likely that the robot's hand will just touch the surface of the box. And at this point, if the hand is just touching the surface of the box, then first, I might not be able to lift the box because of its gravity. And at the same time, the friction between the hand and the box might not be enough. Right. But with contact labels, we can use that contact information to adapt the behavior of the wrist. For example, my target wrist position can be inside the box. Even though the actual wrist position is outside the box, the target is inside, which means I apply a bit more force to lift the box. That was our original intention for adding contact. Of course, in that SceneBot paper, they actually have many different representations for contact. They consider contact from interacting with objects and also contact from interacting with the environment. Interacting with objects refers to things that are movable in our environment, while environment contact like terrain is immovable. So they actually consider contact quite comprehensively.
Yeah. You mentioned contact labels are represented by 0 and 1. I have two questions. First, if we are pulling a drawer, how do you think the contact label would be designed? Is it still 0 and 1? And another question is, when we handle flexible objects, do we still use 0 and 1 for contact labels, or do you think contact labels are enough to solve this problem? Yeah.
Right. Let's split this into two parts. First, regarding the drawer issue you just mentioned, I think if we want to consider a drawer, our contact label might change. We definitely wouldn't just consider the wrist contact label. If we are using hands, I might consider 5 fingers. And for a gripper, I might consider the contact of the gripper's claw part. Right. So we definitely have to change the representation of the contact label. And as for whether it has to be 0 and 1, I think 0 and 1 is one way. But for example, if we have tactile sensors, they will have readings, and those readings actually correspond to contact. We simply binarize it. Right. So whether it's 0 and 1 is probably not a very critical issue. Yeah. Right. But there are multiple ways to represent this contact. Right. But when it comes to deformable objects, I think the contact label, the contact information is still important, but it might not be as obvious because it could be related to the deformation of the object itself. If I only have a binary label, it may be difficult to represent some of the states that arise during manipulation.
Yeah, okay, got it.
Right. But for example, if I want to pinch some plasticine or mold it into a specific shape, then a 0 to 1 contact label might not be very suitable. I might need a continuous value to better manipulate the plasticine and roll it into the shape I want. Yeah.
Okay, I see. Now, speaking of which, I'm actually more curious about how you would evaluate this decoupled dynamics kinematics framework looking back. What are its pros and cons?
By decoupling dynamics and kinematics, say, if my high-level policy outputs kinematics, then in many cases, I essentially just want to do some tracking tasks. And if I assume the object is a rigid body, then there's definitely no problem, and the task can be executed normally. But if we consider more complex objects, then directly tracking the kinematics might not be very useful. For example, if I want to open a door, in the process of opening the door, I actually need to adapt to the forces of the door, right? But if I only have the kinematic motion, it might not adapt that well.
Yeah.
Right? Because, for instance, the part applying force isn't just my wrist, it might also include other parts of the body. Yeah. And then if I want to manipulate some deformable objects, but right now I only have kinematics, it's basically like, how do I follow this motion? But the state of the object itself is something that's probably hard to get with kinematics, or even if I can get it, during the manipulation process, there might be some changes that are different from what was expected. And it's even hard to collect this kind of kinematics data based on a pipeline like VIOK, because during rendering, I actually have a kinematics motion, and I need to know what kind of changes this kinematics motion will cause to the object. When collecting data, since physics isn't involved, it's pretty hard to know that. So even the rendered RGB images have big issues, yeah.
Okay, got it. Okay. And about this separation of kinematics and dynamics, actually, it's already been explained pretty clearly. And another concept you mentioned earlier regarding SceneBot, you mentioned it's a global tracking policy. And I'm also quite curious, how should we understand global tracking, including its difference from local tracking? Could you explain that to us?
Right. Sure, no problem. Yeah, actually, for most tasks, doing local tracking is enough. For example, say I want to dance, and actually what we care about most, to some extent, whether we dance well or not, we'll look at, hey, our movements, like, say for now, I don't consider the position of this robot in the world coordinate system. I just consider the coordinates of each joint relative to the robot's center position. And as long as each joint, like relative to the robot's center, its position relative to the robot's root position is correct, to some extent we can know that, hey, the dance pose is pretty good, right? But here, sometimes when I'm dancing, I need to consider the movement part. For example, if I'm dancing, I go left first and then right. And if it's local tracking, then it might not track this behavior of going left first and then right very well. But if it's global tracking, you can probably track it much better, which means you'll pay attention to the robot's position in the world coordinate system. Right. That's the difference between local and global, mainly in this aspect. Of course, you might think, then why doesn't everyone just use this global tracking policy, right? But this global tracking policy is like this. There are some difficult problems for robots, one of which is called state estimation. And it becomes like, hey, how do I estimate, say, the robot's position in the world coordinate system or the robot's linear velocity? These are all quite difficult. Yeah. You might need to use some, say, Kalman filter or some other methods to solve this kind of problem, right? So if you do these estimations and they are inaccurate, then your global tracking policy might not work very well either, right? And if you estimate these things accurately, then your results will be pretty good. Yeah. So it becomes like whether you can have a good state estimation is a key issue. Yeah. And in SceneBot, SceneBot mainly uses super odometry to do this, as like maybe giving a global coordinate information, which is relatively accurate. Yeah. Because we also use it in VIOK, right?
I see. A quick question. Is there any hardware difference between global tracking and local tracking? For example, do you need to add more sensors to achieve global tracking? Is there such an issue? Or is it just an algorithm thing?
I think it's mainly in the state estimation part, like how you get the robot's ego position. I think there might be some differences there. Right. For example, for this part, currently you have like different ways like VIO, which is through vision, plus maybe the IMU to do ego position estimation. And you have IO, which is through IMU to do ego position estimation. And you can also do it through like maybe LIO. I don't know if it's called LIO, which is through LiDAR and the IMU to do ego position estimation or fuse different sensors together. There are many different kinds of methods. Right.
Okay, got it.
Right, of course, the accuracy of each method might also have some differences, but since I'm not an expert in this area, I'm indeed not that familiar. Yeah.
Like this super odometry, does it use VIO or which method?
For super odometry, there is LiDAR based. Yeah.
Oh, LiDAR based.
LiDAR based, and there should be IMU based. Yeah.
Super odometry? I mispronounced the name.
Okay, another quick question I'm quite curious about. Does mobile manipulation need global tracking more than dancing or something from your perspective?
Actually, I don't think it's necessarily the case.
Oh, okay.
Yeah. It becomes like if your policy, like say you have a high level policy and you output your kinematics motion, and if the motion you output, its feedback is relatively real time, then actually your low level local tracking policy doesn't need to be changed to global. Just to give an example, say your robot is currently doing a task and you find it's going off course, and now your high level can give you real time feedback to get you back on track, then actually you don't really need global tracking. Yeah.
Okay. Then what do you think drove the development of global tracking? Like, what is the motivation for people to do global tracking? It's more accurate, so it won't go off course, or it doesn't need real-time correction.
Right. It's like it's more accurate, and then for example, it has lower requirements for real-time correction from the high level. Right. And then sometimes, like, say my data is completely generated in simulation, right? And then actually, to some extent, it might lack some like error correction capability. For example, if you kick the robot really hard and it's already completely OOD, but at this time, your high level might also find it hard to correct the robot's position back. So at this time, if you are a local tracking policy, then it might not be so suitable. Yeah, but if it's a global tracking policy, you kick it hard, it can still correct itself. At least at the low level, it can correct it. Yeah.
Oh, okay. Got it. That's about it for my quick questions about the paper itself. And there are some questions I find more interesting that I'd really like to ask you. Like, after finishing this paper, what is your biggest takeaway? Yeah. And another question is, what are some things you didn't think were that important before, but after finishing it, you feel are very important?
I think my biggest takeaway is every part of the system is actually very important. Yeah. And you can't ignore any part. Yeah, because robotics is actually a multidisciplinary field, and our pipeline actually includes data generation, training a VIOK policy, and then system integration, and various sim to real gaps and latencies. I think all parts are very important. Actually, at the beginning, we might think that our motion synthesis pipeline can generate kinematic motions, and as long as they look plausible, we initially thought the tracking policy should be able to track them. But later we found out it's not, like its feet still have to be on the ground and its hands still need to like maybe carry the box. We need to have relatively high requirements for this kind of quality. Yeah. And so it became like we need to like constantly refine our, including at the beginning, our Gaussian splatting quality was also not that good. And then plus we also had some like sim to real scale, like maybe the distances of the scenes and stuff were not aligned, and these issues led to us having a period of time where our sim to real was always not doing very well. Yeah. So I think every part of the system, the whole system, we actually need to control it well and pay close attention to it. Yeah.
I have another quick question. Like looking at the development of the humanoid industry, are there any underlying technical changes or core research that drove it and also made VIOK possible? And from your perspective, which research is very important?
First, let me answer about the humanoid part. And I think the emergence of motion tracking played a huge role. Yeah. And from beyond Mimic to Sonic, a general motion tracker. Internally at Amazon, we also have SceneBot this time. And actually, I think motion tracking is like what changed the development of this industry. Yeah. And like in the past, if we were based on reward, maybe doing reward design for individual tasks, then actually we might need to, like for complex reward design, say it's a long horizon task, then I have to design the reward individually for each stage. And after motion tracking came out, actually we can just give a piece of motion reference and then the robot completes the task. Yeah. And another part is for humanoids, I think RGB sim to real is also a very important point. Yeah. And it can make this humanoid robot. In the past, we might have not considered environmental perception. For environmental perception, previously, many works might have been based on depth or based on elevation maps, but they might lack some understanding of semantic information. Yeah, but now we have RGB sim to real. And then for VIOK, actually, I think VIOK, I can use a few different keywords to explain. First, for VIOK, we do a real to sim. Yeah, real to sim is like we do 3D reconstruction of the real scene, and then in simulation. And the emergence of Gaussian splatting is actually very important. For example, Gauss-Gym and other work related to Gaussian splatting. Yeah, and at the same time, because we do some motion synthesis, and including our motion synthesis also includes like maybe human object interaction, HOI, and we follow Jauman's prior work, such as human object interaction from human level instructions. Yeah, and I think whether it's real to sim or maybe some motion synthesis in graphics and humanoid sim to real actually deeply influenced our VIOK work. Yeah, because of the development of these three fields, it made it possible for us to do this work.
Great. And then back to this grand question of humanoids, like I'm quite curious, what problems do you think are still unsolved in humanoid academic research, and which one do you think might be the easiest or the first to be solved?
I think like how to better handle, but I think many of them are those like more general problems. For example, for this kind of long horizon, for those like maybe relatively long horizon tasks, how do I do a better task planning? I think might be a point to consider. And another one is like when the robot encounters some failure modes, how does it recover? For example, in VIOK, we generate our kinematics data. And essentially, during the generation process, there won't be any failure mode data generated. But if we really encounter this situation in the real world, how does the robot recover? I think this will be a challenge to consider. Yeah. And yeah, I probably mainly have these problems to be solved. Of course, there are many, many more, but maybe we can explore them together in the future.
Okay, no problem.
Right.
And another question is about data, because in my impression, maybe manipulation had a big development because there was a lot of progress related to manipulation data, including Aloha, including Wumi. I don't know about data collection in local manipulation or humanoids. Of course, you shared a lot earlier. What do you think it might look like in the future, or what do you think is a relatively ideal data form?
Right. Actually, I don't know either. Yeah. I think the highest quality data is probably real world data, where you just go out and collect a ton of it in the real world. And then you use that data to train a model really hard because, like you said, the physics and all the dynamics, everything is correct. So you won't have any RGB gap. Yeah. But because of that, you'd probably need a whole body teleoperation pipeline like Sonic. Yeah. But The main thing is, if you're talking about collecting this kind of whole body data, it's really time consuming, labor intensive, and quite a hassle. So another direction is like, can we transfer this UMI data to a humanoid? Right, right. But if you want to transfer UMI data like that, you probably still need a pretty good low-level tracking policy. With UMI, when you're collecting data, you might be recording the coordinate positions of the two grippers and their open/closed states. So you'd also need a policy that can track the coordinates of both hands. Like it could be a 2-point, 3-point, or even a 5-point tracking policy. Yeah, right. And then the third one would be VIOK. But with VIOK, the angle is probably a bit different from the first two. It's more about generating synthetic data from a simulation perspective. But as I just mentioned, the advantage is that compared to the first two, it can generate a ton of data much faster and more efficiently. Right. And basically, I think this data should be able to transfer from sim to real. But I think one issue is that some things are really hard to simulate or even represent from a kinematics perspective, like changes in objects. So in that kind of situation, VIOK might not be the best choice. Though maybe there will be new research in the future to address these limitations.
I'm quite curious, after doing VIOK, what kind of research do you want to do next? What's the research direction?
I feel like the first thing is currently with VIOK, we're mostly considering tasks like carrying boxes. In the future, we might consider whether VIOK can do humanoid plus gripper to manipulate smaller objects, or if we can apply the VIOK idea to manipulation in general. Yeah, I think these are all directions we might want to push forward. And then the second thing might be, like I just mentioned, how to handle it if the object isn't a rigid body, or if we can introduce a small amount of real-world data to solve this limitation of VIOK. Yeah.
Okay, great. Those should be all the core questions about your thoughts on your paper. And this podcast has a traditional segment, which is to ask a question for the next guest. You actually already know who the next guest is, so you can leave a question for him or multiple questions, and I'll pass them along.
Yeah, sure, no problem. I probably have a few questions. The first one would be, if we've pretty much solved the low-level motion control for robots now, what do you think is the biggest bottleneck for general-purpose humanoid robots? That's the first question. And the second question is, what would be the most suitable way to scale this data, whether it's for tabletop manipulation, dexterous hands, like for grippers, dexterous hands, or for humanoid robots? How to scale it would be best. And yeah, can I ask anything?
Yes, you can ask anything.
Oh, what was the biggest difficulty and bottleneck you encountered during your PhD? That is, during your PhD, what do you think was the best, most successful choice you made, and what was the most failed choice you made?
Sure, I'll pass that along. Okay, thank you so much, Yen-Jen, for your time. I feel like I've learned a lot, and thank you so much for being the guest on my very first podcast episode. All right, that's it for this episode. Okay, I also wish Yen-Jen all the best in the future and hope to see more of your academic work come out.
Okay, thanks.
Thanks. Bye-bye. Have a great holiday.